Hello, my name is Jennifer and I'll be presenting about human behavior in ad hoc teamwork. To start off, ad hoc teamwork is a multi-agent problem in which agents must try to collaborate with one another without having prior communication about the goals of each agent. Within ad hoc teamwork experiments, there have been many different optimizations to enable autonomous agents to better predict what each agent is doing. We chose to take this problem and see how humans would act when collaborating with other agents in ad hoc settings. This is important as we see people becoming more integrated with technology, specifically robots and other artificial agents. Furthermore, this will allow us to create a different optimization for autonomous agents working with humans under these conditions. Because humans will not always act the most efficiently, our end goal is to create a model of human behavior. This model can then be used to better predict how humans will act in ad hoc situations. In order to see how humans act in these settings, we utilized a specific ad hoc teamwork setup called the tool fetching domain, where we placed one human and one autonomous agent to work together. We tested 3 conditions with differing levels of instruction about the collaboration possible with the autonomous agent. We measured the participants' performance in terms of optimality and legibility. To look more specifically at the domain in which our participants were in, here's an example of one of the setups. We begin with the possible goals positions, green and red. There is a worker agent or doctor who must go to one of these stations as specified by some instructions. Let us assume the doctor's goal room is the green one. There is also a fetcher agent or robot nurse who must get the correct tools for the doctor at the tool station room. The robot nurse does not know what the doctor's goal room is initially, but tries to determine the goal based on the doctor's path. We chose to put the human in the worker's position because it will allow us to see if they choose to collaborate with the fetcher and create a model with the actions the humans take. In this instance, the doctor has many choices as to how to get to the green room. This orange path is an example of an optimal path. This means that the path is the minimal number of steps the doctor must take to get to their goal room. This purple path is an optimal path and legible path. Not only is the path the minimal number of steps to the goal station, but it also shows the robot nurse where the doctor's goal room is as soon as possible. With the orange path, the robot nurse does not know which room is the correct room until the doctor takes the move to the left after 4 steps. On the other hand, with the purple path, the robot nurse knows the goal is the green room after the doctor takes his first move to the left. This is because the red room is on the right, and assuming the doctor is acting optimally, the green room is the only possible room the doctor is going to. Under different instances of this domain, we wanted to see if people would choose to take optimal or legible paths. We were able to identify optimality based on the number of steps the user takes to the goal. For legibility, we utilized a legibility time step. A legibility time step is the number of steps above the minimum number of steps necessary for a path to be legible. The minimum number of steps to be legible in this scenario is 1. Thus, the purple path has a legibility time step of 0 because the user took the correct step to be legible as soon as possible. On the other hand, the orange path has a legibility time step of 4 because the worker took 4 steps to take a move that will allow the fetcher to know what the goal is. We had 3 conditions in which we tested. The first of these is the baseline condition. Under this condition, the participants were only given simple instructions that mention what their goal was as a worker, but did not mention that the fetcher agent is trying to predict where the worker's goal was. The second condition we had is the incentive condition. Under this condition, we included the same instructions as the baseline condition. However, we added bolded text in the initial screen that mentioned a bonus for the top 10% of participants. We also included bolded text in the instructions mentioning how the fetcher agent is trying to predict where the worker's goal is. These instructions can be referred to as local information as defined by Huber. Local information is instructions that provide a general description about the task. So in this scenario, we provide a general description about the fetcher with hopes that the worker will collaborate with the fetcher. Lastly, we had an instruction condition. Under this condition, the participants received the same basic instructions, incentive, and local information as with the previous conditions. We also included more bolded text in the instructions, dictating that the main goal of the worker is to act in such a way where the fetcher can predict where the worker is going. These instructions can be referred to as global information, also as defined by Huber. Global information provides specific information about the task, and in this scenario, we provide information about how the worker should act in order to collaborate with the fetcher. For each of these conditions, the participants partook in 16 different instances of the tool fetching domain, some of which are displayed here. We separated these instances with different sizes, number of stations, and which station was the goal station. These instances also have differences in how to act optimally and legibly. If you're interested in learning more about this experiment setup, please go read our paper. Now I'll show our results. One of our measures of user performance was optimality. In this graph, we showed the average path length above optimal per experiment for each condition. The average path length refers to the average steps participants took to get the correct workstation. We standardized this across the different setups by comparing it to the minimal or optimal number of steps a participant could take. An average path length above optimal of 0 means that all human agents for that experiment perform optimally, whereas an average path length above optimal of 1 would be, on average, the participants took one more step than optimal. We utilized a one-tailed paired t-test in comparison to an artificial optimal agent. This test was one-tailed because participants could not have a path length that is better than optimal, and it was a paired t-test because we compared each point with an artificial optimal agent as if an optimal agent had completed the experiment itself. Based on this t-test, we found that under all conditions, the human participants significantly deviated from optimal. This means that humans did not always choose to be optimal within this experiment. The other measure of user performance was legibility. In this graph, we show the total number of workers that took each legibility time step. This allowed us to standardize across the different experiments where someone required the participant to take at least 2 steps to be legible. In this graph, the closer a curve is to the y-axis, the more legible people are in that condition. With the large view towards the left of the graph, it shows that most participants will act legibly as soon as possible. We conducted a chi-square test and compared the number of workers taking the minimum number of actions to be legible and the number of workers taking more than the minimum. We compared each condition with each other, and there was not a significant difference between the baseline and set condition, meaning there was no improvement in legibility once given the incentive and local instructions. However, there is a significant difference between the baseline and instruction conditions, meaning that humans act more legibly given global instructions. As a summary, we initially wanted to see how humans behaved under ad hoc teamwork settings. In order to test this, we had 3 different conditions and measured the results based on optimality and legibility. As a result, we found that humans would not always act optimally, but they would act more legibly given explicit instructions on how to act. The next steps that come from this experiment is seeing if we can model human behavior. This will allow us to create a fetcher agent that can better predict where the human agent is going. On a larger scale, it will also allow us to investigate if we can design artificial agents that can collaborate more efficiently with humans. Thank you for listening to my presentation about human behavior in ad hoc teamwork. If you would like to read our paper, you can scan the QR code that links to the paper. Thank you.